look at worksheet number 24 that was for homework last night, starting with question number 2. This says 222.86 something, a little bit of a typo here because really we should have had the element symbol there. If you look at your periodic table, you would find that that 86 atomic number was radon, although it doesn't really matter here. You can still solve this question without knowing what element it is. Radon undergoes decay, produces this alpha particle and something else, this ionizing radiation that we call alpha particle, and something else, some other, what we call a daughter nucleus. How do we figure out what we're producing here, the daughter nucleus? Well, we have to balance out the atomic number and the mass number. So let's do the mass number first. 4 plus 218 gives me 222. 2 plus 84 gives me 86. And what's atomic number 84? PO, polonium. So there we go, 218 polonium. Now, is there anything else produced here? Like a neutrino or an antineutrino or anything like that? Nope, that's it. Okay, that's it. You could get gamma decay occurring after this, right? Because gamma decay occurs, you remember, when you have an excited nucleus. It's excited as a result of something else having already happened. Alpha decay, beta decay, something else has already happened. But don't worry about that right now. Okay, that's a separate process. That's a consecutive phenomenon taking place, not a concurrent phenomenon. So it's not taking place at the same time. It's a secondary thing that takes place. And you're never going to have to balance one with gamma decay because gamma decay is 0, 0, right? There's nothing to balance when the gamma particle is 0, 0. By the way, alpha decay occurs, if gamma decay occurs as a result of an excited nucleus, alpha decay occurs when the repulsive force is too big, beats the attractive force, and the repulsive force is too big when you have too many. What is it that repels each other? When you get too many protons relative to the number of neutrons, the repulsive force or electrostatic force is bigger than the attractive force of the strong nuclear force, and it ends up breaking apart. All right, next one we want to go over is number 3. 3 has lead 214 decaying into bismuth 214 plus something. Let's say 214 plus 0 gives me 214. 83 plus what equals 82? Probably one of the most common mistakes that are made in this unit. What's the answer there? Minus 1. And of course, the answer that people put for this one a lot, probably a quarter of people on a test will put plus 1. Okay, 83 plus 1 is 84. 83 plus minus 1 is 82. That's what we're looking for here. What kind of particle is that? That's a beta particle. You call it an electron as well if you want. It's exactly the same thing. What else is produced here? Yep. Good. It would be an antineutrino. Whenever you have beta negative decay, you get an antineutrino produced. Whenever you have beta positive decay, you get a neutrino produced as well. And by the way, this one occurs as a result of having too many neutrons. Those neutrons don't repel each other to the point where we're going to break the nucleus apart. Rather, if you have too many neutrons relative to the number of protons, then the nucleus is energetically unfavorable. So that means that a neutron ends up changing into a proton and an electron. So what happens here? Look, you had 82 protons, now we get 83. Why do we have an extra proton? Because a neutron changed into a proton, and look, an electron that ends up getting kicked out of the nucleus there. Next one we want to go over is number 4. 4 says uranium-234 goes to 42 alpha plus something. 4 plus 230 gives me 234. 2 plus 90 gives me 92. And atomic number 90 is, I should know that one. Thorium. Okay. Anything else produced there? No, that would be it, right? After that alpha decay, that's alpha decay, right? After alpha decay, you could get gamma decay, but that's a secondary thing. 6. Lead 208 plus something gives me HS, whatever that is, 265 plus a neutron. We go through the same process here. It's just that we have to add up some things on the right side instead of the left. 265 and 1 is 266. 208 and 58 is 266. 108 and 0 is 108. 82 and 26 is 108. So what is this? Atomic number 26? I believe if you check your periodic table, it's iron. Fe. 58. Now, the other ones were a little bit simpler. Number 4 was alpha decay. Number 3 was beta negative decay. What's number 6? Alpha, beta, artificial. This is going to be an artificial transmutation. Basically, if you've got a couple things on the left side, we're going to call it artificial. We're going to, tomorrow, come up with some specific names for a couple of those. But right now, let's just stick with artificial. It's not radioactivity. Next one, number 10. We're going to say beryllium 9 plus hydrogen 1 goes to lithium 6 plus something. 9 plus 1 is 10. 6 plus 4 is 10. 4 plus 1 is 5. 3 plus 2 is 5. What's this? It's an alpha particle or a helium nucleus. Call it whatever you want. It's the same thing. We're going to call this alpha decay. No, we're not going to call this alpha decay because this is prompted to happen, right? This is an artificial thing. I mean, it could happen naturally, but it could also happen artificially by us literally firing a hydrogen nucleus at beryllium and causing it to temporarily fuse and then break apart. 13 is our next one. Hg. What was Hg? I can't remember. Mercury? Mercury? Mercury 210 goes to beta particle plus something. 0 plus 210 minus 1 plus 81, not 79, 81. And what is that? Is that TL? Anything else? If you've got beta negative, there's always what else produced? An antineutrino, yeah. The neutrino is matter, albeit incredibly light matter. An antineutrino is antimatter. It's the antimatter equivalent of it, just like a positron is the antimatter equivalent of an electron. We would call this what? Artificial alpha beta. This would be specifically beta negative. Good. And finally, let's take a look at number 14. Nitrogen 14 plus an alpha particle goes to oxygen 17 plus something. 14 plus 4 is 18. 17 plus 1 is 18. 7 plus 2 is 9. 8 plus 1 is 9. What's 1, 1? Hydrogen. That's normal hydrogen, right? Regular hydrogen, the most common isotope of hydrogen. There are other isotopes of hydrogen, as you're going to see later today, but this is the most common one. What do you call this? Is this alpha decay because you get an alpha particle there? No, it's not. It's not decaying into an alpha particle at all. It's being bombarded by an alpha particle. We're firing alpha particles at the nitrogen 14. So this isn't alpha decay at all. This is what we call an artificial transmutation reaction, which could also happen naturally, but we'll call it artificial. All right. If we're good with this, and I hope we are, because I guarantee you're going to see more than one of these on your unit test. More than one that you have to balance on your unit test. And I'm pretty sure you're going to see more than one of them on your diploma exam as well. These are gimme questions once you know how to do them. They're gimme questions, right? Just be careful that you don't mess up the -1 and the +1 thing, the neutrino and the antineutrino thing. If we're good with these, then we're going to move on and talk about how quickly these reactions take place, or the rate at which these reactions take place. I want to define a term that's going to help us to determine how quickly these reactions take place. The term is half-life. And half-life means the time that it takes statistically, I'll tell you what that means in a second, for 1/2 of a radioactive sample to decay. The time that it takes statistically for 1/2 of a radioactive sample to decay. Let's say we have carbon-14. Carbon-14 has a half-life of 5,730 years. Half-lives can vary, by the way, from tiny, tiny fractions of a second to millions of years. This half-life happens to be 5,730 years. That means that, on average, statistically, 1/2 of whatever amount of carbon you have will have decayed in 5,700 years. Here's the reason. In a certain amount of time, every nucleus has a 50% chance of decaying. Let me give you an analogy for that. If I flip a set of coins, let's say 1,000 coins, they're all heads. They start off as heads. Okay, heads is carbon 14. They start off as 1,000 carbon 14s. I flip them. Each one of those coins has a 50% chance of decaying into a tails, right? After I've flipped them all one time, statistically, how many heads am I going to have? 50%, right? So because each nucleus in 5,700 years has a 50% chance of decaying, then on average, or statistically, half of them will have decayed in that amount of time. If I start off with 10 kilograms of carbon 14, after 5,700 years, I'll have statistically 5 kilograms left. If I start off with 160 nuclei, it's not a math, it's just a number, then on average, after 5,700 years, I'm going to have 80. If I start off with 100%, then on average, after 5,700 years, I'm going to have 50%. If I flip those 1,000 coins, is there anything to say that I cannot have 499 heads and 501 tails? Not at all. They each have a 50% chance of decaying, which on average means 50% of them will decay. But we know that statistics don't always work out, right? Statistically, when I buy a lottery ticket, I'm not going to win. There's a 1 in 14 million chance of me winning a lot of 649. But of course, deep down, we all know that I am going to win at some point. Statistics don't always work out. Flip 1,000 coins, 500 times on average, 500 times out of 1,000, you're going to end up with heads, and 500 times you're going to end up with tail. But you could end up with 499 and 501. You could even end up with 450 and 550, although that wouldn't be likely, right? You could even end up with 1,000 tails and 0 heads, couldn't you? It's not very likely, but it's possible. When we crunch numbers with half-life, we're using statistics, probability. Understand that that's not an exact science. The bigger the sample size, the better. If I flip 1,000 coins, the more apt I am to be at 50% than if I flip 4 coins. But even still, there's no guarantees. Understand this final point before I give you a couple equations to describe this. What I'm doing with you today is not a simplification. I'm not dumbing things down because you guys aren't smart enough to get this. I'm not saying that we're going to find the statistical average or statistical analysis because you guys aren't smart enough to know the way it's really done. If you had a PhD in physics, you would do it the same way. This is a natural, this is a spontaneous, this is a, what's the other word? Flip a coin, 50-50 chance of heads or tails. That's a random process. Even if you have a PhD in physics, you can't do any better than we can. Predict based on probability what you're going to end up with. The only time you know with certainty is after it's done. All right, I'm going to give you a couple equations to describe this. The first one does not appear on your data sheet, but it's a pretty easy one. N, little n that is, which stands for the number of half-lives. If the half-life is 5 years and 15 years have gone by, that's 3 half-lives. If the half-life is 4 seconds and 8 seconds have gone by, that's 2 half-lives. Little n is the number of half-lives. And we can find that by dividing the time by the half-life. 15 years have gone by, the half-life is 5 years. 15 divided by 3 is 5. The half-life is 4 seconds. 8 seconds have gone by. 8 divided by 4 is 2. 2 half-lives have elapsed. That equation isn't on our data sheet, but it's a pretty logical one, right, that we can just come up with on our own. The number of something, the amount of something, is equal to the total divided by the amount for 1. The total time divided by the amount for 1 half-life. The second equation, a lot of you are probably going to recognize. As I explain it, even more of you will probably recognize it. N, big N that is equal to n subscript 0 times 1/2 to the little n. How many people recognize that one from math class? This would be exponential decay. If you wanted exponential growth, you would change the half, right? Change the number half into something else. This one is on your formula sheet, yes. N, of course, stands for the number of half-lives. N0 stands for the initial amount, how much we start with. And the initial amount can be measured in pretty much whatever units you want. It could be kilograms. We start with 1,000 kilograms of carbon-14. It could be grams or any unit for mass. It could be just a number, 1,000 nuclei. It could be a percent. If it's a percent, what is NO almost always going to be if it's a percent? NO is going to almost always be 100, right? You're almost always going to start with 100%, and you're going to end up with something less than 100%. It could be even a rate of decay, decays per second. We start off with 10 decays per second. After one half-life, only 5 of them are decaying per second. Another set of units, I wouldn't worry about what this means, but I want to just write it down to illustrate something. A BQ, a becquerel, means a decay per second. Same thing as decays per second. The only reason I write that down is not because you have to know that unit, but rather just because if you're doing one of these questions and you see a unit that seems somewhat not familiar to you, it seems kind of foreign to you, it's probably going to be big N or big N0. Right? If you see a unit for time, it's probably going to be pretty familiar to you. Seconds, days, hours, years. If you see a non-familiar unit like BQ, becquerel, it probably means an amount, which means it's going to be N or N0. So N0 is the initial amount, and any of those units, N would be the final amount. And of course, what's the only thing that you got to pay attention to for the final amount? Same units. Yeah, same units, whatever they are. One other little thing that you should remember as a check, the final number, N, should always be bigger or smaller than N0. Always smaller. Always smaller. Now you do your math and it should work out to be that way, but as a check, you should pay attention to the fact of whether it's smaller or bigger. Just to make sure you've done it right. Okay, we're going to do a couple examples today. One for right now, and then we're going to set you to work on a few questions for a little while, and then we're going to do another example a little bit later on. First question is on the sheet that I handed out to you earlier today. Example number 1, it says the half-life of hydrogen-7 isotope is 2.3 times 10 to the negative 23 seconds. Carbon-14 was 5,700 years that it took half of them to decay. Hydrogen-7, 2.3 times 10 to the negative 23 seconds. So clearly you can see that the half-lives can range dramatically. What is hydrogen-7, by the way? This is normal hydrogen, 1 proton and how many neutrons? 0. 1 proton, no neutrons. Hydrogen-7 is this. It's an incredibly rare isotope of hydrogen that has 1 proton and 6 neutrons. Now, if you were to make water with hydrogen-7, could you, by the way, make water with hydrogen-7? If you had enough of it, you could. Chemically, it's identical to hydrogen-1. It would react with oxygen and everything else in the exact same way, because really chemistry is electrons, right? It's dealing with the electrons, and that is no different. The charge is no different. It would just be heavier. You would still have H2O. It would still chemically be identical to what we usually have as water, except the water would literally be heavier, quite a bit heavier. All right, so we've got this incredibly rare amount of hydrogen-7, 27 grams of it, which would be pretty much impossible to come up with 27 grams of something that was this rare, but it is what it is. How much of it would remain after this many seconds? What do we got here? My half-life, T1 half, is 2.3 times 10 to the negative 23 seconds. My initial amount, this is what I start with, 27.0 grams. That's an amount, grams, kilograms, becquerel. percent, an amount. How much would remain? How much would be left, the final amount, after this much time? 1.84 times 10 to the negative 22 seconds. Here's what you want to do. Get the value of little n. T over T1 half, which is 1.84 times 10 to the minus 22, divided by 2.3 times 10 to the minus 23. Can we stick with the units that we have here, seconds? Could I have gone minutes? Sure, it doesn't matter as long as it's consistent, right? I believe when you do that, I think it works out to be 8. Anybody has that? 8 it is, yes. We get 8 half-lives have elapsed here. Now let's say the final amount is equal to n0 1 half to the little n, which is 27.0 grams times 1 half to the 8. Now, follow me on this one, okay? Because this one is a calculation that we've never done in Physics 30 before. It's not hard, but if you're not familiar with it, maybe you make a mistake on your calculator. We're going to say for this one 27 times 0.5, not 0.5 times 10 to the minus 10 to the 8, but rather just 0.5 to the 8. There's no times 10 to the anything here. This is a 0.5 to the 8 rather than 10 to the 8. We do this, we end up getting 0.105 or 1.05, or we'll say 1.1 times 10 to the negative 1 grams. So we start off with 27 grams, and after 8 half-lives, we're down to 1/10 of a gram. You can maybe see why there's not very much of this stuff out there, why this is incredibly rare. The half-life is 10 to the minus 23 seconds. You're down to 1/10 of a gram if you start it with 27 grams after 10 to the minus 22 seconds. It doesn't last very long. Well, it doesn't disappear, it transmutates into something else, right? It becomes something else. This would be most likely beta negative decay. I don't want to say that with certainty, but it would almost certainly be beta negative decay. Remember, beta negative decay occurs when you have too many neutrons. And there's a lot of neutrons here, right? 6 neutrons, 1 proton. So hydrogen 7, assuming it does undergo beta negative decay, which I think that it would end up producing, what would that be? Helium 7? Make sense? So it's not like it's gone, it's just transmutated into something else, which in itself sure has a lot of neutrons, right? Although the ratio is twice as good as it was before, that would still almost certainly undergo beta negative decay. Like which ones undergo beta negative? The half-lives? Oh, I don't know where you'd find that. I don't know where that would occur. All right, I want you to take a look at worksheet number 25 now. There's a number of questions on that page, or sorry, on that worksheet. It extends on for a number of pages, actually. For now, I want you to simply look at questions 1 to 8. We are going to go a little bit further with it, but for now, number 1 to 8 are going to relate to the example that we just did in class. The second and final example that I want to do with you today is example number 2. It says the half-life of plutonium-244 is 8 times 10 to the 7 years. We just went from 10 to the minus 23 seconds for H7 to 8.0 times 10 to the 7 years for polonium-244. So you can see such dramatic differences in half-life for these different isotopes. How much time must pass before a 1 kilogram of sample of plutonium-244 decays to 62.5 grams? And remember, of course, this is all statistically how much time needs to pass. We don't know for sure how much time needs to pass until after it's passed and the event has taken place. But we can predict, based on probability, that it'll be a certain amount of time. So what do we got here? We've got a half-life, T1 half, is 8.0 times 10 to the 7 years. We've got an initial amount, N0 is 1.00 kilograms, and we've got a final amount, N is 62.5 grams. Now, I do want to be in the same units here, grams, kilograms, doesn't matter which. I think it's easier to multiply by 1,000 here and get 1,000 grams than it is to divide that by 1,000. Get 0.0625 kilograms, but whatever, doesn't matter. We're looking for t, little t. We're going to say n is equal to t over t1 half because it's the only equation that has a little t in it. And we multiply little n by t1 half, but we don't know what little n is. Okay, so we're going to try to find out what little n is. And we're going to do that by using this equation. N is equal to n sub 0, 1 half to the little n. And we're going to rearrange this to solve for little n. How are we going to do that? How are we going to solve for little n there? Yeah? Yeah. How many of you guys are familiar and comfortable with logarithms? How many of you guys hate logarithms? I always hated logarithms. I'll tell you what, the good news is the curriculum objective in Physics 30 says that you need to be able to perform, and I quote, simple, non-logarithmic half-life calculations, which means that even though in this question it looks like you need to use logarithms, there is always another way. Doesn't mean you can't use logarithms just because they say you need to perform simple non-logarithmic calculations. It doesn't mean that you're never going to come across a question where you can use logarithms, but it just means that you don't have to. Okay, let's do it the logarithm way, and then I'll give you the backup way for those of you who don't like logarithms. We're going to say n is equal to log n over n0 over log 1 half. And I'm not going to go through that process of explaining that because if you're not comfortable with it, then I want you to leave it. It's not something that you have to be able to do in Physics 30. If this makes sense to you, what I just did, that's great. Go with it. If it doesn't, that's fine. 62.5 over 1,000 over log 0.5 gives me, I believe when we do this, I think we got 4. Wasn't it? Let's just go through this on a calculator just to make sure that you guys can follow along with it. Log 62.5 divided by 1,000. And let's divide that by log of 0.5. Gives me 4, sure enough. So now I can say 4 times the half-life of 8.0 times 10 to the 7 gives me 3.2 times 10 to the 8 years. Don't like logarithms? There's always another way. The other way is what I call the divide by 2 method. So we're going to make a little table in the divide by 2 method. And the little table is going to look like this. We have 2 columns, n and n, little n and big N. After 0 half-lives, little n is number of half-lives, right? After 0 half-lives, I'm left with 1,000 grams. Nothing's happened. After 1 half-life, what do I have left? 500 grams. After 2 half-lives, I've got 250. Keep dividing by 2. After 3 half-lives, I've got 125. After 4 half-lives, I've got 62.5. So it's 4. Right? Either way you look at it, it's 4 half-lives. And of course, you're going to end up with the same answer at this point, regardless of how you got little n, the number of half-lives. Now, this logarithm method is certainly a more versatile method because it allows little n to be anything. The divide by 2 method only works if little n is a whole number, right? But because you're not required to do logarithmic half-life calculations, little n in this context where you've got to find it will be a whole number. Does that make sense? So don't worry about that. Okay, if you're comfortable with logarithms, that's great. If you're not comfortable with logarithms, that's okay. Just use the divide by 2 method, get the number of half-lives that way, and do your thing. So red or green doesn't really matter. Okay, it's like you're colorblind here. Got it? All right, so here's what I want you to do now for the rest of the class. And you got about 8 or 9 minutes to do that. Finish up questions 1 to 8 on that worksheet that I had already assigned. In addition, I want you to do the next 2 questions, questions 9 and 10. So you're on worksheet number 25, I think it was. Is that it? Number 1 to 10 for homework now. See what you can get done in class and maybe not have very much homework tonight.